Welcome to Lecture 17, in which we will now begin to talk about Chapter 5, and we'll be concentrating primarily on gates. But before we get to the gates, I do want to consider one other topic which is relevant to Exercise 5.2, in which asks about the existence of a cloning operator for various sets of states. And in particular, in Part A of that exercise, you are asked to find out whether or not there is a cloning operator for this set of states, consisting of the 0 state and the 1 state. So let's understand what a cloning operator is, and then make an observation that will help us to understand this problem a lot better. Okay, so we're going to suppose that U is a unitary transformation. And we say that U clones the state C. Now this is just a definition. U is said to clone the state C if U of C0 is equal to C. Now, this information alone, plus the fact that U is unitary, leads to an interesting observation that will help us with this problem. So the observation begins as follows. We're going to suppose that U clones the two states, C and Phi. So U clones two different states, C and Phi. Now let's see what we can do with that information. Okay? Well, we're going to calculate the inner product of U of C0 with U of Phi 0. And don't try to figure out why we're doing this. It's just, it will turn out, as we'll see in the end, that this is a convenient thing to do. But for right now, we don't have any particular reason to do it. Well, because U is a unitary operator, it preserves the inner product. Now what that means is that the inner product of U of C0 with U of Phi 0, which is what we have here, is simply going to be the inner product of C0 with Phi 0. That's what we mean when we say that U preserves the inner product. So it is simply because U is unitary that we're able to go from this line to this line. Now for the definition of the inner product, when we have a 2-qubit state like this, remember that we'll take the inner product of the first bits. So we have the inner product of C with Phi and the inner product of 0 with 0. That's the inner product of the second bits. And of course, a 0 inner product with itself is equal to 1. So we're just left here with the inner product of C and Phi. And this would be true now for any unitary transformation. This line here would be true for any unitary transformation. We have not yet used the fact that U clones the states C and Phi. But now we will use that information. Okay, now once again, the statement that U clones C means that U of C0 is equal to C. So since U clones both C and Phi, then the inner product of U of C0 with U of Phi 0 will be the inner product of C with Phi. And once again, now this is true because remember that U clones C. So U of C0 is C, and U of Phi 0 is phi, because U clones both psi and phi. So this is what we get when we use the fact, let's just make sure this is very clear. When we go in this direction, we're using the fact that U is unitary. But here, we're using the fact U clones psi and phi. Okay, now, using the definition of the inner product for a 2-qubit state again, just as we did and going from here to here, we can do that again here, and we will get inner product of psi phi with the inner product of psi with phi. And now, look at what we have at the two ends of this long equation. We have, and of course we have obtained this quite quickly, but we have that the inner product of psi with phi is equal to the inner product of psi with phi multiplied by the inner product of psi with phi. And of course then this means that the inner product of psi with phi can only have two possible values, and that is 0 or 1. So in doing all of these problems, we can immediately look at each set, and it must be true that the inner product of the different kets with each other must be either 0 or 1. If that's not true, then there cannot possibly be a cloning operator for that set. Now, in this case, when we look at, so now we're ready to actually do problem A, or 5.2a, and we see that for these two, if we think of 0 as being psi and 1 as being phi, then this does satisfy the requirement that the inner product of those two states is 0. So we cannot rule out the possibility of a unitary transformation existing in this case. And in fact, one does. Now, to find, so we'll say what unitary transformations will clone these two states. Well, we really only know two pieces of information. The transformation will clone 0 and it will clone 1. Now, the fact that it clones 0, so maybe I should write this out for you. All we know is that U clones 0 and U clones 1. So, going back to our definition of what it means to clone a state, this means that U of 0, 0 is equal to 0, 0, and U of 1, 0 is equal to 1, 1. Those are the two pieces of information that we have, and that's it. But we know also that U must be unitary. And so, fortunately, this information alone is enough to let us get some possibilities. For instance, the fact that U of 0, 0 is equal to 0, 0, recall that 0, 0 is represented by the vector 1, 0, 0, 0, and so the fact that u of 0, 0 is equal to 0, 0 tells us that the first column of our matrix for u must be the vector corresponding to the image of 1, 0, 0, 0, which is 1, 0, 0, 0. And the fact that the second, here we have u of 1, 0 is 1, 1. Well, remember that 1, 0, the state 1, 0, is represented in vector form by the vector. Well, let's just review this here. Okay, so 0, 0 is represented by the vector 1, 0, 0, 0. 0, 1 is represented by 0, 1, 0, 0. 1, 0 is represented by 0, 0, 1, 0. And finally, 1, 1 is represented by 0, 0, 0, 1. Okay, this is what we've learned before. So, as I said here, the fact that u of this first one is equal to this, that means that u of the vector 1, 0, 0, 0 is 1, 0, 0, 0. So we're going to get 1, 0, 0, 0 here in the first column of u. Now, what is this next piece of information when we transfer it to vector form? Well, 1, 0 here, this ket corresponds to 0, 0, 1, 0. This 1 is in the third row. So when we look at the action of u on that, it's going to tell us about the third column of u, and that third, what do we get? We get 1, 1, which is 0, 0, 0, 1. So the third column of u will be 0, 0, 0, 1. And now we just need to, for the second and fourth columns, we need to pick these so that we don't, we still have a unitary matrix. And remember that for a unitary matrix, that all of the columns must form an orthonormal set, and all of the rows must form an orthonormal set. So we have some possibilities. One possibility, U1, some, let me say, easy possibilities. These are not the only ones, but these will do. One easy possibility then would be the following. Notice that all of these rows are of length 1, and they are all orthogonal to each other. And likewise, all of the columns are of length 1 and are orthogonal to each other. So this and they have the two columns here that match this information are present. So this would be one possibility. Of course, there are others. Now, all of them must have the first column equal to 1, 0, 0, 0, and must have the third column equal to 0, 0, 0, 1. But we could have also said 0, 1, 0, 0, and 0, 0, 1, 0 here. And this would have worked as well. And once again, notice that the different rows are all of length 1 and all orthogonal to each other, and the different columns are all of length 1 and orthogonal to each other. So here would be a couple of easy possibilities, and you could get others as well, but just remember that the first column must be 1, 0, 0, 0. The third column must be 0, 0, 0, 1. And all of the columns and all the rows must have a length of 1, and all the rows must be orthogonal to each other, and all the columns must be orthogonal to each other. So that would be the way that you could do part A of exercise 5.2. And I think I'll just leave that at that point. And now we'll begin to talk about gates. And this course will begin to look a lot more like computer science. So the first gate that I'd like to mention, if you look at page 75 of your text, you'll see a number of gates defined, but one that I want to call your attention to particularly is the one labeled X, which has the matrix representation 0, 1, 1, 0. And so you can see that this is a transformation. It acts on a 1 qubit state, and it would take the 0 ket to the 1 ket. How do we know this? Because the 0 ket is 1, 0. So since there's a 1 in the first entry and a 0 in the second entry, we want to look at the first column of X. And what is this first column? It's 0, 1, which corresponds to the ket 1. So this transformation would take the 0 ket to the 1 ket, and the 1 ket to this, which is of course the 0 ket. So this is one important transformation that we'll be dealing with quite a bit. And another is the Hadamard transformation, which is defined in this way: 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, minus 1 over square root of 2. And so you can see that this transformation will take the 0 vector to 1 over square root of 2 times the 0, it'll take the 0 ket to 1 over square root of 2 times the 0 ket plus 1 over square root of 2 times the 1 ket, which is of course the same thing as the plus ket in the Hadamard basis. And it will take the 1 ket to 1 over square root of 2 times the 0 ket minus 1 over square root of 2 times the 1 ket, which is the same thing as the minus ket in the Hadamard basis. So here are two transformations that both act on single qubit states and that will play an important role in several of the examples that we'll look at. Now, before we go to transformations of 2 qubit states, I want to make one point here about the 1 qubit states and 1 qubit transformations. Let's suppose that we had a circuit that operates on 1 qubit states that looks like this. What would be the matrix? What is the matrix representation? Well, The way that you should look at this circuit, it's exactly the same as what you've always done with circuits of this type. For instance, even classical digital systems will go from left to right. And so the idea is that we will have some state C entering from the left and going to the right. And notice that the first transformation that will act on C is X, and the second one that will act is H. Therefore, if we want to write this out as write the action as a matrix equation, what we would have is something like this. C would be transformed into this. Notice that X is acting on C first, and then H will act on the result of that. So the point here is that as you're reading from left to right, these boxes go in the order X, H, but in the matrix equation, they will go in the order H, X. So just remember how this ordering goes when you write your matrix equation. And of course, now that you know that for the matrices that the correct order is HX, it would be easy to answer this question, because you would just say HX is equal to 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, minus 1 over square root of 2, and then X is 0, 1, 1, 0. And so the answer to this problem would be 1 over square root of 2 when we multiply here, and then another 1 over square root of 2, and then minus 1 over square root of 2, and 1 over square root of 2. So the net effect would be to take the 0 ket to this, and of course this corresponds to the minus ket in the Hadamard basis, and the 1 ket would be taken to this, which is the plus ket in the Hadamard basis. So it's definitely quite important that you understand this ordering for this problem. And by the way, if you wanted to just figure this out without even writing equations, you could say, okay, remember we just said that the 0 ket will go to the minus ket, and the 1 ket will go to the plus ket. If you wanted to see that looking at the circuit, okay, let's suppose that we have the 0 ket coming in here. Remember, X takes the 0 ket to the 1 ket. So the 0 ket would go to the 1 ket, so we'd have the 1 ket here, and then H takes the 1 ket to the minus ket. So sure enough, overall, when we have the 0 ket coming in, we have the minus ket exiting, which is consistent with the fact over here that the minus ket is the first column. And on the other hand, if we had the 1 ket coming in, okay, X takes the 1 ket to this, which is the 0 ket. So the 1 ket would come in, it'd be transformed to the 0 ket, and then H takes the 0 ket to the plus ket. So overall, the 1 ket would go to the plus ket, which is consistent with this. So either way you look at it, either by looking at the circuit diagram or by doing the matrix equation, we arrive at this same result, that overall this will take the 0 ket to the minus ket and the 1 ket to the plus ket. So those have been some transformations on single qubit states. Now let's look at transformations on 2 qubit states. And the first that we want to look at is the C0 gate. The C0 gate, or also called the controlled NOT gate, has the following symbol. Now it acts on two qubit states, and it looks the symbol for it is this. And the way that the controlled NOT gate works is the following. First of all, you should think of this line, again, this works on two qubit states. So the top line works on the first qubit of the state, and the second line works on the second qubit of the state. And the way that this C0 gate works, it will do the following. The 00 ket will be sent to the 00 ket. Likewise, the 01 ket will be sent to the 01 ket. But the 10 ket will be sent to the 11 ket, and the 11 ket will be sent to the 10 ket. In other words, the first bit is acting as a control bit for what's going to go on with the second bit. And so if the first bit here is 0, then the second bit does not get changed. You see, in these two cases, the first bit is 0, and so the second bit is 0 there and 0 there, 1 here and 1 there. There's no change. But when the first bit is equal to 1, then the second bit will get toggled. So 1 0 goes to 1 1, and 1 1 goes to 1 0. Notice that in every case, the first bit remains the same. It's just the second bit that may or may not get changed, and whether or not it gets changed depends on the value of the first bit. So an interesting question here is to ask, well, what would be the matrix representation of the C0 gate? Well, just as we did before, remember that 00 ket corresponds to the 1 0 0 0 vector, and that's going to go to itself. So the first column of this matrix is 1 0 0 0. Okay, the 01 ket will correspond to the vector 0 1 0 0, and that will also be taken to itself, so that means that the second column of the matrix will be 0 1 0 0. Now 1 0 here, the 1 0 ket corresponds to the vector 0 0 1 0, and 0 0 1 0, which has a 1 in the third entry, so we're going to be looking here at the third column, that goes to 1 1. And the vector corresponding to that is 0 0 0 1. So we must put 0 0 0 1 here. And then finally, 1 1, which, as we've just said, is 0 0 0 1, goes to 1 0, which is 0 0 1 0. 0 0 1 0. So this is the matrix representation of this 2-qubit transformation that is achieved by the C0 gate. To understand how this is used, let's look at the following problem. The book says that this circuit, and by the way, this is on page 80, the book claims that this circuit will take the 0, ket to 1/2 of 0 plus 10 plus 0, 1 minus 1. And so our goal now will be to understand how that is the case. And remembering our ket is coming in from the left, and so the first qubit, that's the top line. The first qubit will encounter this Hadamard gate, and at the same time that it's encountering the Hadamard gate, the second qubit is traveling on undisturbed until we get to this point, and then both qubits will encounter this controlled NOT gate. So let's think about what would happen to a qubit, and try to understand then what we need to do. Okay, so we're going to look at this first stage first. We have H for the first qubit, and the second qubit remains unchanged. So let's try to find a matrix representation for just this portion of the circuit. Well, we know that if we had the 0 ket enter, in fact, what we want to do is to find out for each possibility. So 0, 0, 0, 1, 1, 0, and 1, 1. We want to know what's going to happen in each one of these cases. And remember, the first thing we can observe is that in each case, the second qubit is unchanged, because we just have a line here for the second qubit. It's only the first qubit that will be changed by this part of the circuit, and it will be changed in accordance with the Hadamard transformation. So this 0 here, remember the Hadamard transformation takes the 0 ket to the plus ket. So we would have plus, and then as we said, the second qubit will just be 0. It's unchanged. Same kind of thinking here. The 0 for the first qubit will go to plus, and the 1 for the second qubit remains unchanged. The 1 for the first qubit, well, the Hadamard transformation takes 1 to minus, And again, the second qubit is unchanged. And finally, the 1 here goes to the minus qubit, and the second one is unchanged. Now let's express each one of these kets in terms of the standard basis. And when we do that, the first one will give us 1 over the square root of 2, 0, 0, plus 1 over the square root of 2, 1, 0. The second one will give us 1 over the square root of 2, 0, 1, plus 1 over the square root of 2, 1, 1. Now remember that the minus in the Hadamard basis, minus means 1 over square root of 2 times the 0 ket minus 1 over square root of 2 times the 1 ket. So we'll have 1 over square root of 2, 0, 0, minus 1 over square root of 2, 1, 0. And then for the last one, 1 over the square root of 2, 0, 1, minus 1 over square root of 2, 1, 1. So now that we know where this transformation will take each element of the basis, now we can find the matrix. And now we've done this a couple of times already, and I hope you're beginning to get accustomed to it. And so I would encourage you to stop the video and try to do this on your own first, and then we'll do it together. Okay, so remember that 0, 0 is represented by the vector 1, 0, 0, 0. And that's going to go to 1 over square root of 2 times 0, 0, plus 1 over square root of 2, 1, 0. So that means that I'm going to notice that all of these terms have 1 over square root of 2. So I'm just going to take that out so that I don't have to write it over and over. So we have 1 over square root of 2 out in the front. And then we have 0, 0. That gives us a 1 in the first entry. And 1, 0 will give us a 1 in the third entry. So the first column, which represents the where the transformation is going to take this vector, or the vector corresponding to that, the first column is going to look like this. And this first one comes because of 0, 0, and the 1 in the third row comes because of 1, 0. Now, what about the next one? Well, we have 0, 1, so that corresponds to a 1 in the second row, and 1, 1 corresponds to a 1 in the fourth row. Now, for the third column, we have 0, 0, so that's a 1 in the first row, and then minus 1, 0, so that's a minus 1 in the third row. And finally, for the fourth column, we have a plus 1 in the second row and a negative 1 in the fourth row. And notice that if you keep into account that we have a factor of 1 over square root of 2 for all of these terms, then you can easily see that each column is of length 1, each row is of length 1, all the rows are orthogonal to each other, and all the columns are orthogonal to each other. in this, which is what we expect from this, which is a unitary transformation. So this matrix represents the action of this part of the circuit. And remember that we're going to operate with this matrix first, because this is the first part of the circuit that encounters our, we have C entering, going from left to right. So this is the first thing that encounters C. So, and our expression, our matrix expression, this will be at the extreme right. Now the next part of the circuit is the controlled NOT gate. Just let me make sure you understand. So we've done now this part on the left, and now we would next come to the controlled NOT gate. And we have already found that the matrix for that will be the following. It leaves the first qubit as it is, and it will, for the second qubit, if the first qubit is 0, it will leave the second qubit undisturbed. But if the first qubit is 1, it will switch the second qubit from 1 to 0 or from 0 to 1. So this is the matrix representation for that part. And then the last part of the circuit is another piece that is identical to that first piece. So if we look at the matrix representation for the entire thing, we will have the following. We'll say entire circuit. Now remember, this will be at the extreme right, because that's what's going to operate on the state first. So I'll have 1 over square root of 2, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, negative 1, 0, 0, 1, 0, negative 1. That will operate first. Then after that, we'll have the controlled NOT gate, which is represented by this matrix. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. And then the last part to operate is this, which is identical to the first part. So we will have 1 over square root of 2, and then 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, negative 1, 0, 0, 1, 0, negative 1. And now we need to calculate what this is equal to. Of course, 1 over square root of 2 times 1 over square root of 2 will simply be 1/2. And then we'll write down the first matrix, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, negative 1, 0, 0, 1, 0, negative 1. And now let's go ahead and multiply the second matrix by the third matrix. So we're going to, when we do that, we will get 1, 0, 1, 0 for the first row, 0, 1, 0, 1 for the second row, 0, 1, 0, negative 1 for the third row, and 1, 0, negative 1, 0 for the final row. And now if we multiply those two matrices together, let's see what we'll get. Okay, multiply this times this, and we'll get 1, 1, 1, negative 1. And then for the next row, we will get 1, 1, negative 1, 1. For the next row, we're going to get 1, minus 1, 1, 1. And finally, for the fourth row, we will get minus 1, 1, 1, 1. And now we can see, of course, the first column, and don't forget this factor of 1/2, but the first column multiplied by 1/2 would be the image of the 0, 0 cat. This would be the image of the 0, 1 cat. This would be the image of the 1, 0 cat. This would be the image of the 1, 1 cat. And so we see that this circuit, takes this circuit takes 0, 0 to 1/2 of 0, 0 plus 0, 1 plus 1, 0 minus 1, 1. And if you compare that to what we said above, this does match with exactly what the book claims. Well, and so that would be the way to figure out what a 2-qubit transformation does, how it acts. So now let's take a look at some problems. Okay, so the first two problems for this lecture are as follows. Both of these deal with cloning, and then the in-class problem or problems will deal with gates. But the first question is simple. It just says, is there a unitary transformation that will clone all the states in this set consisting of the 0 cat, the 1 cat, the plus cat, and the minus cat? And the two possible answers are simply yes and no. And then in 17.2, you were asked to circle each that will clone all the states in the set consisting of the plus cat and the minus cat. Now, I'm asking you, these matrices are all with respect to the to the standard basis, which is what we've been doing in class. And I will advise you that it might be a little difficult for you to, it'd be great for you to try, but you might find it difficult to figure out exactly how to arrive at these matrix expressions, or the correct ones. There's at least one correct one. It might be hard for you to arrive at it directly, but for this case, because it's a little trickier than what we've done up here. Here, in the case that we did at the beginning, okay, in this beginning problem corresponding to exercise A, we said what unitary transformations will clone these two states. And so we could find the first column of the vector, the first column of the matrix and the third column of the matrix directly, because we knew the image of the 0, 0 cat and the image of the 1, 0 cat. So this gave us these, the first column and third column of our matrices. But in this case, from the fact that this transformation that we're looking for, from the fact that it clones the plus cat and the minus cat, well, that doesn't tell us exactly what it does with the, it doesn't tell us directly what it does with the 0 cat or what it does with the 1 cat. And therefore we can't immediately derive what the first column or third column of the matrix will be. So you may find this a little difficult to try to derive the matrix, but what you can do for each one of these matrices down here, you can, well, first you would probably want to check that each one is unitary, and you would find out that it is. In each case, and remember, in these two cases where we have 1 over square root of 2 out front, that means that multiplies all of the terms in the matrix. And so for each matrix, you would find that each row is of unit length, each column is of unit length, and each row is orthogonal to all the other rows, and each column is orthogonal to all the other columns. So all of these are unitary transformations, and you have to decide which ones clone these two states. And remember, cloning the state means the fact that it clones plus means that it would take plus 0 to plus plus, and the fact that it clones the minus means that it would take minus 0 to minus minus. So you need to figure out which of these transformations would do that. Maybe more than one, but identify which ones will do that. And then, as I mentioned, we'll have some more problems in class. So that's it for Lecture 17, and good luck.